Hi. I want to continue our discussion of Chapter 21 and electric potential. And so I mentioned in one of the previous lectures about a new unit, an electron volt. And I have said that it's sort of a atomic size unit of energy. So it is just a unit of energy, so we can convert directly between joules and electron volts using this conversion. But some of you may have noticed that this number looks familiar. 1.6 times 10 to the negative 19th joules. Well, this number, the magnitude here, is 1.6 times 10 to the negative 19th. Recall that that is the charge of an electron. If it's positive, I guess it's the charge of a proton, but that is the fundamental charge. And so this leads to sort of the definition of what an electron volt is. Like, why do we use this instead of just some other measure? And so an electron volt is the potential energy, is the kinetic energy gained by an electron as it accelerates through a potential difference of 1 volt. Which is kind of weird to think about. It's also the potential energy of an electron, of a proton, sitting at 1 volt. So the potential energy that a proton has sitting at 1 volt, that's 1 electron volt. An electron would have negative 1 electron volt of energy if it was at a location where the potential was 1 volt. So it's a little bit strange, but it is a very useful unit. We've already seen this. This is a review slide. Inside of a parallel plate capacitor, we see that we have a constant electric field. And thus far, that's kind of how we've introduced capacitors in this chapter, or in this class, is a capacitor is something that creates a uniform electric field. So within this parallel plate capacitor, we have a uniform electric field. And we've been given an equation. It's Q over epsilon naught A is the equation for our electric field within a parallel plate capacitor. Recall this epsilon naught is simply a number that makes all the units work out, and it's related to K. Right, so we've got K and epsilon naught, both constants. All right, so all that's review. Let's remember, though, that it takes work to move a positive charge from the negative plate to the positive plate of this capacitor. Now, since it takes work to push that charge across the capacitor, where does that work go? Well, it must be going into potential energy of that proton. So as I push this proton across from one side to the other of the parallel plate capacitor, then its potential energy increases. Well, it must be moving to a region of higher potential then. So we see that the potential also changes within a parallel plate capacitor. And so within a parallel plate capacitor, here's sort of 4 different ways of visualizing that potential. It does go from low potential here to high potential here. In other words, I am pushing the charge uphill. Recall, the potential is like a height in our electrical landscape. So if we were to just plot the potential as I move from one side of the capacitor to the other, we would see that it forms a straight line. It is linear. So we see that a uniform electric field gives rise to a linearly changing potential. And since the potential is the same everywhere across some line in here, right? Then we see that we could kind of create these surfaces here that represent equipotential surfaces. In other words, this is a surface that everywhere along there is at the same potential. So the negative plate is at 0 volts. The positive plate is at 1.5. And in between, it varies uniformly from 0 to 1.5 volts. And it does so the same way, whether I move here to here at the top of the capacitor or here to here at the bottom of the capacitor. Again, everywhere inside the capacitor has the same functional shape. This is what happens when we have a uniform electric field. So here we've just simply plotted distance across the capacitor and potential. Here we're showing these equipotential surfaces. Surfaces of equal potential is how we could describe that. And here we've seen sort of a side view of this, where now we're sort of mapping where the potential is the same. So everywhere along this line right here is 0.5 volts, and everywhere along here is 1 volt. And now we can kind of combine these views this view and this view here and sort of create this almost three-dimensional plot here, where we've got distance here and distance on this axis, and then sort of in a vertical axis we see the potential varying. Now, if we've got a uniformly varying potential as we move from the negative to the positive plate, we end up with a linear equation. So this here is just a little bit of algebra to get to the punchline, which is basically here, the change in voltage is equal to the electric field times the change in position. Now, this equation makes it seem a little trickier than it is, right? Notice that if my potential varies from 0 at the negative plate to 1.5 at the positive plate, then if I'm halfway through the capacitor, what's my potential? Half the potential difference in the total capacitor, right? So if I'm halfway through this particular capacitor, I'm at a potential of 0.75. If I'm a third of the way through, I'm at 1/3 of the total potential, or 0.5 volts. If I'm 2/3 of the way across the capacitor, then I'm at 2/3 of the potential, or 1 volt. Again, it varies linearly. We do have this equation, it works every time, but I think proportional thinking makes it a little bit more straightforward, honestly. Now, this is the potential inside a parallel plate capacitor. Now, why do we care about parallel plate capacitors at this point? Because they create a uniform E field. So indeed, this equation will work inside a parallel plate capacitor every time, but it will also work anytime we get problems where we've been described a uniform E field, or an approximately uniform E field, in which case we can still use this equation. So just a real quick example, and this should help us to understand a little bit more about that unit that we were using also. So in the figure, so I've got this capacitor here. We've got 0 volts here. We've got 300 volts here. And I'm going to ask a series of questions. So first of all, in this figure, which capacitor plate is the positive plate? Well, the high potential is positive. So it's the 300 volt side that is the positive side. Okay, so the 300 volt is the positive plate of my capacitor, and the 0 volts is the negative plate of my capacitor. Now, what is the electric field strength inside the capacitor? Well, let's jump up here. Notice we've been given this. Delta V equals E times delta X. Let's write that down. Okay, so in this case, we've been given delta V across the entire capacitor. We've also been given the distance across the capacitor, and so we can calculate the electric field strength. What we need to do first is do some algebra, isolate E. So E equals delta V over delta X, and so that is 300 volts divided by 3 millimeters, or 3 times 10 to the negative third meters. And so when we get this, when we run our calculator, then we get a value of 100,000 volts per meter. So there's our answer. Again, this equation does work anytime we've been given a uniform or approximately uniform electric field. Now, here's a tricky one. What is the potential energy of a proton at the midpoint of the capacitor? Well, we know that we have this equation. The potential energy is simply equal to Q times the potential. And so what we could do is we could just crank through this. And I guess that's what we'll do first, is we'll just do a brute force calculation. We know that the charge of a proton is 1.6 times 10 to the negative 19 coulombs. And if it's at the midpoint of the capacitor, what is the potential? Answer that to yourself. Hopefully you said 150 volts, because if I'm halfway through the capacitor, then I'm at half the total potential. So that means that the potential at the midpoint of the capacitor is 150 volts. And so if we crank through this, we get a number, and that number is 2.4 times 10 to the negative 17th joules. Okay, and that's a perfectly acceptable answer. However, do notice it's a very, very small number, right? 10 to the negative 17th is a very small amount of energy. If there was a smaller unit of energy to use, we might get a nicer number. And indeed, that's what an electron volt is a smaller unit of energy, which will give us a nicer number. But not only that, we can be real slick about this, right? So looking back at our PowerPoint here, we see that if a proton's at the midpoint, then it's at 150 volts. Well, how much potential energy does a proton have at 150 volts? 150 electron volts. That's the utility of that unit. It makes things real easy. So we could just simply write down, what is the potential energy? 150 electron volts. A lovely answer. Completely correct. Because an electron volt is defined as the potential energy that a proton has when it's sitting at 1 volt. So how much potential energy does a proton have when it's sitting at 150 volts? 150 electron volts.